Howdy folks, so this last video for this chapter will build on our previous video about precipitation reactions. This one will cover the other two major driving forces, acid-base neutralization, which will be very brief, and oxidation reduction, which, while will be brief, will be covered more intensely next semester. Let's go ahead and get started. So we'll be ready to go and so we'll be out of here. Okay. So acid-base neutralization is a reaction where an acid and a base will cancel each other out. The byproduct of the majority of acid-base neutralizations will be water and a salt. The salt is just the leftover parts of the balancing ions. Now that salt could be insoluble, but most of the time it will be a soluble salt. But so examples, nitric acid, HNO3, potassium hydroxide will come together to form potassium nitrate, which is soluble, and H2O. Or you would have written HOH, but H2O. If I break this down into its total ionic form, you'll see that H plus and nitrate and potassium plus and hydroxide go to potassium and nitrate and water. Writing the net ionic equation means this simplifies to H plus and OH minus, go to water liquid. One of the key features here is the water liquid. Water liquid. Liquids, solids, and gases do not break apart. So that is why the H plus and OH minus do not get canceled out. So the fact of the matter is that almost all net ionic equations for acids will end up simplifying to this. There is one major exception, and that is with weak acids and weak bases. I will not directly test you over many of these, but the fact of the matter is sometimes these come up on homework. A weak acid or weak base is a weak electrolyte. So when it dissolves, it spends more time as a compound than as a cation-anion pair. So hydrocyanic acid, which is one of the weak acids, will not break apart. And so even though the sodium will break apart and simplify, the hydrocyanic acid will not. And so what we must start to recognize is whether we have a strong acid or a weak acid. I'm going to quickly list the strong acids real quick. If it's any of these acids, it will break apart. HCl, HBr, HI, HNO3, H2SO4. This one specifically breaks apart into H plus and HSO4 minus. And the other big one that will come along rather commonly is HClO4 and HClO3. Any of the perchlorate, perchloric acid, chloric acid, perbromic acid, periodic acid, those guys typically, but these guys are our major strong acids. Any acid that is not one of these acids is going to by default be considered weak. So HF is going to be strong. HF is going to be weak. H2S is going to be weak. H2CO3, weak. HC2H3O2 acetic acid, weak. HCN, weak. H3PO4, it's weak. HClO2, HClO1, H2SO3, HNO2. All these guys are examples of weak acids. H3PO3. So weak acids. It's easier to remember the strong ones. And this isn't even all the weak ones, but this is the majority of the strong ones. So if it's any of these unusual ones, it's weak and it would not break apart. But as I said, I usually don't test over that. Now, another class of reaction is one that is a gas-forming reaction. Occasionally, some aqueous products of a double replacement will be unstable and will then decompose to form a gas. So we're forming a double displacement and then a decomposition. This can be the driving force, or it could be a driving force in addition. So for example, carbonic acid by itself is not super stable and will break apart into water and CO2. Hydrogen sulfurous acid is unstable and will break apart into water and SO2. Ammonium hydroxide can break apart into ammonia and H2O. So if I were to react NH4 ammonium chloride with sodium hydroxide, you'd form sodium chloride and ammonium hydroxide, but it will produce water and ammonia, and so that's going to drive this forward. It's going to drive this forward because typically, if you talked about this reaction down here in terms of precipitation, you don't have a precipitation. Ammonia is always soluble with hydroxide. Sodium is always soluble with hydroxide. Ammonium is always soluble with chloride. But when that breaks apart into ammonia gas and water, well, that's going to keep this from flipping backwards because the ammonia is going to float away. It's going to leave. You can't capture it once it's left. It makes it really hard to go backwards. Now the last driving force is one called a redox reaction. The redox reaction involves the change in the relative oxidation states of the elements via a process called oxidation and reduction. Oxidation, among other things, is the loss of electrons. When you're losing a negative electron, the atoms get more positive. Typically, an atom that gets oxidized gains oxygen, usually. Reduction is the gain of electrons. Because you're gaining electrons, it becomes more negative because we're reducing the charge by giving it negative things. However, a redox reaction must always have both parts. Just like an acid base needs an acid and a base, a redox reaction needs both the reduction and the oxidation. If you cannot find both, it is not redox. There is a rather easy mnemonic to help us remember these. Oil rig is one of the ones I use. Oil stands for oxidation is loss of electrons. Rig is reduction is gain of electrons. So whenever you're wondering which one is oxidized, it's the one that's losing electrons. So when you're looking at a chemical equation and you're trying to figure out whether an oxidation has occurred, we want to determine the charges of all the atoms. And you're looking for whether an atom has changed its charges from one side of the arrow to the other. Now, the charge of each element, we can either do it the element by itself or the element within a compound. but that is the oxidation number or the oxidation state. Now these rules are mere guidelines to help speed up the process. I don't expect you to memorize them all, but because some of these are pretty straightforward. Once you recognize what I'm going at, it makes sense. Rule 1. All pure elements, whether it be a diatomic gas or the element by itself, any pure element has a net charge of 0. It has to have 0 because it's not charged. And so if it's not charged and by itself, it matches just the neutral state. So a charge of 0. If I give you any monoatomic ions, they must have the oxidation state equal to their charge. So sodium plus 1 is plus 1. Calcium 2 plus is 2 plus. Chloride 1 minus is 1 minus. If you have an ion by itself, you know its charge. Now, remember, the sum of the oxidation states within a formula is equal to the charge of the formula. So, if you have CO2 neutral, it means the sum of the carbons and the oxygens must add up to 0. If you have carbonate, which is CO3 2 minus, the sum of the carbons and the oxygens must add up to -2. With that in mind, these last 4 things are guides. Hydrogen is almost always plus 1. The only exception is when it's bound to a metal, where it must be -1, because metals are almost always positive. Oxygen is almost always -2. The only major exception is called a peroxide, and it's usually indicated by something really obvious. But the peroxide is a O2 2 minus. So oxygen, it's 99% of the time it's safe to assume oxygen in a compound is -2. All group 1 metals will be +1 in a compound. All group 2 metals will be +2 in a compound. Aluminum will be +3 in a compound. Zinc will be +2 in a compound. Silver will be +1 in a compound. Cadmium will be +2. Those metals that only ever had one oxidation state will only ever be that oxidation state within that compound. We've already learned how to name them, so you should not have forgotten them so quickly. Halogens are almost always -1 in a compound, especially fluorine. If there is more than one halogen, it's almost guaranteed to be -1. If it's the center atom, well, things change. But if it's the outer atoms, it's almost always -1. Every other element can be determined by context by adding up these charges, keeping these simple facts in mind. You can do that, you can find the charges. If you find a single change, you know it's a redox. So, with that in mind, let's practice finding the charges of such elements. Some of these guys will be easy. Some of them will be a little bit trickier. Some of these guys are charged, so that makes it a little harder. I'm just writing them down real quick. It'll take me about a minute. But we have potassium renate, we have magnesium Dichromate. We have okay. My iron magnetite. Okay, with that in mind, let's look at these guys. Potassium is group 1. So it's going to be +1. How many potassiums are there? There are 3. The total charge is 0, so if that is +3, what's that going to be? That is going to be -3. So phosphorus is -3, potassium is +1. This guy is group 2, 2+. If you don't already recognize, hydroxide is -1. However, we pull that up. Oxygen is typically -2. So -2 times 2. H is +1 times 2. 1 times 2 is 2. Plus 2 is 4. 4 minus 4 is 0. -2 plus 1 is -1. Hydroxide is -1 because 1 and -2 makes -1. I may not know this guy. I may be able to do this, and this might work, but one way to do it. Oxygen is -2. -2 times 3 is -6. There's 2 irons, so this must be +3. 3 times +2 is 6. It's balanced. +6, -6. Nitrate. I don't know nitrogen. Well, I do know nitrogen, but I'm going to assume we don't know nitrogen. -2 times 3 is -6. The total charge must be -1 because it is charged up here. X minus 6 is -1. If I add 6 to both sides, X must be +5. +5. This is net 0. Oxygen, we're going to assume -2. -2 times 2 is -4. Carbon is 4 plus. -4, +4 adds up to 0. Once again, we got -2. I'm going to pretend I don't know what sulfur is. -2 times 4 is -8. X minus 8 is -2. If I add 8 to both sides, X is +6. Is it a coincidence that nitrogen is group 5, carbon is group 4, sulfur is group 6? No. It's not a coincidence on these cases. The highest oxidation state relates to their group. We cannot have higher than +4 on carbon. We cannot have higher than +5 on nitrogen. We cannot have higher than +6 on sulfur. It's simply the truth. Now we got a little bit harder. Even though it's net 0, potassium is 1, oxygen is 2 times 4. So we have rhenium is the unknown. 1 minus 8 is -7. So rhenium must be +7. Because 7 plus 1 is 8, minus 8 is 0. Magnesium is 2 plus. Oxygen is 2 minus, but times 7 is 14. 2 chromiums. Here's the hard part. 2 chromiums. -14 plus 2 is -12. -12 plus 2x equals 0. So each chromium is +6. plus 6 times 2. So it's 6 plus. Now here's the only really challenging one. Oxygen is negative 2. So that's negative 8. Does 8 evenly divide by 3? And the answer is no. The only way this works is if you have 2 3 pluses and 1 plus 2. This is a weird compound that is made up of these two elements. Magnetite, which is the partially oxidized but still magnetic form of iron, is made up of FeO, which is 1 iron 2 plus, and 1 Fe2O3, which is iron 3 plus. 3 plus 3 is 6, plus 2 is 8. 8 minus 8 is 0. As I said, that's the only one that's really massively challenging. The rest of these are straightforward. Now, with that in mind, common redox reactions. The simplest redox reaction you can ever recognize is a single displacement reaction or single replacement reaction. These are by definition a redox reaction. Why? A single displacement or single replacement reaction is one where an element is converted into a compound and a compound is swapped to form an element. Anytime you have a pure element, it has the charge of 0. Anytime a pure element goes from 0 to not 0, it has been oxidized or reduced. Anytime an oxidation or reduction has occurred, it's a redox reaction. So if you recognize a single displacement reaction, you know it is redox. However, many combination or decomposition reactions can also be redox, but they do not have to be. Also, all combustion reactions must be redox because they use a pure element, oxygen. So if you can recognize that, that will help you notice the driving force. As I said, in every redox reaction, one element must be oxidized and one must be reduced. Here's where terminology can be a little tricky. Because one element is oxidized, it must be causing a reduction somewhere else. So the element who is oxidized is called the reducing agent. The element that is reduced oxidizes another element, and so it is an oxidizing agent. Oxygen, for example, is an oxidizing agent because it oxidizes other things. In the reaction below, chlorine is reduced, aluminum is oxidized, so chlorine is the oxidizing agent of aluminum, and aluminum is the reducing agent of chlorine. Here are some simple redox reactions. I'm going to skip past number 1 first and look at the other 3 because they are dead giveaways. So oxygen and carbon monoxide goes to CO2. Even before you look at charges, you have the pure element oxygen, meaning we're going from 0 to 2 minus. Yes, there is an oxygen already at 2 minus, but now there is another set of oxygens at 2 minus. Carbon is being oxidized from 2 plus to 4 plus. Next one's a little hard. We have hydrogen peroxide goes to water and oxygen. You might not recognize that hydrogen peroxide is 1 minus, but oxygen is a pure element, and thus oxygen is going from 1 minus to minus 2 and from 1 minus to 0. You may not be able to recognize that it's peroxide, but we're forming a pure element means it has to be a redox. And then aluminum, solid, pure element, and iron 3 goes to iron, solid, pure element, and aluminum 3. Oxygen remains 2 minus, but aluminum gets oxidized to 3 plus, and iron gets reduced from 3 plus to 0. So let's go back up to the previous guy. If you can recognize any oxidation, the other must be there. So chromate is a little bit harder to do unless you remember the one we just did. But iron 2 oxide that's 2 plus. The next guy is iron 3 oxide, that's 3 plus. Iron is being oxidized. So, that's because chromium is being reduced. If we go through our charges, chromium shows up as 6 plus in our dichromate example. It's going from 6 plus to 3 plus. And so it is being reduced in this case. However, if you can recognize one charge change, you know you got it. One more slide before, I guess, one example. And so this is activity series. Not all redox reactions will occur all the time. We have to do a swap, but the driving force is not so simple. But basically, there's two atoms at high energy state, and when they swap electrons, they each go to a lower energy state. So not all swaps will occur all the time. If they're not both in the same energy states, they won't swap. Now, as I said, all single displacement reactions are redox, but not all single displacement reactions will occur under the same conditions. So calcium, if I put it in water, I get calcium hydroxide and hydrogen gas. No problem. Cobalt, water won't work by itself. I have to put it in strong acid, hydrochloric acid, and it forms hydrogen gas. The reaction of the metals with an acid is called corrosion. Now, not all, as I said, not all the single displacement reactions will occur, so we can categorize them on reactivity based on an activity series. So what we see here is a list of metals that can be oxidized by acid. That the following metals in the yellow block work with cold water. We just put them in water and boom, they react. The next one need boiling water. It needs steam, but they will, boom, react. Magnesium, aluminum, manganese, iron will react to produce steam to form hydrogen. The light blue block need a acid to make it react. So cobalt, lead, tin, nickel need an acid. And then you notice H2. That is the element that is being formed when I react. So H2 is there. Everything below H2 will not react. Everything above H2 will react. So everything below H2 will not react with water at all. Copper is neutral in water. Silver is neutral in water. Lead, platinum, gold is neutral with water. Even in acid, they will not react. There's a reason why copper, silver, and gold are precious metals that we tend to make our money out of. They're not going to react with acids or water to easily dissolve. They're not going to react with these to easily dissolve, so they're going to be safe. But basically, looking at this table, any metal that is higher on this table will act as the reducing agent of any metal lower on this table in a compound. So iron is in the green block, copper is in the dark blue block. So iron will reduce copper and get oxidized itself. If I mix the reaction around, literally flip it around, it will not occur. So I just swapped it back. Say it will not swap back. So if I look at this series, we can predict which guys will replace which guys will react with what. So real quick, recognizing reaction type. So just a quick practice to finish this off. I'm not even going to go to doc cam. What do I see here? The first guy, CH3CO2H, that is acetic acid, whether you see it or not, and NaOH. They form, that's sodium hydroxide, they form H2O, which is our water, and sodium acetate. What do I see changes? The CH3CO2 stays the same on both sides. What we have is the H and the OH come together to form water. The H and the OH come together to form water, so this must be an acid base. Now, just because there's water or a base present does not mean it's acid base. As we see in example 2. 2 sodium plus 2 water forms hydrogen gas and two sodium hydroxides. We have a pure element, sodium, converting to another pure element, hydrogen. This is a single displacement reaction in its finest. Thus, it is a redox reaction. Sodium is going from 0 to +1. Hydrogen is going from +1 to 0. And finally, sodium hydroxide undergoes a double displacement with magnesium chloride to form magnesium hydroxide and sodium chloride. Okay, there's no water forming. If I check the charges, there's no positive or negative charges changing. And if I check the table, would say hydroxides are almost always insoluble except for rule 1 and barium. So barium is soluble, but magnesium hydroxide is not. Magnesium hydroxide is a solid, and so it is a precipitation type reaction. Most of these guys, I would say, consult a table. But if you can recognize H and OH transferring or an element changing, it becomes a lot easier. But the table is almost always necessary when you're talking about precipitation reactions. With that in mind, I am done. Have a good day.